Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to be going over how to predict the products of electrolysis, in particular the mixtures of cations or anions. So let's get into this. So I'm going to go over a couple of examples. In my last video I showed you how to predict the products of a molten salt through electrolysis. And so here, what happens? Well, that was a pure salt. It wasn't a mixture. It was just one salt with only one cation and one anion that are mixed together in the cell. But what happens when you have two different salts mixed together? What do you do then? So I'm going to go over a couple of examples. So example number one is, what if I have two salts in which they have the same anion but two different cations? So I have to figure out what's going to undergo oxidation, what's going to undergo reduction. Well, in this case, figuring out what's going to undergo oxidation is pretty simple because I only have one anion. So the anion is going to undergo oxidation, so it's going to lose an electron. But here I have two cations, so I have to figure out which of those cations is more likely to undergo reduction. And so here we don't really have the reduction potentials of molten ions, but we can still use the electrode potentials, the reduction potentials of the ions in solution, so dissolved in water, aqueous. So although the electrode potentials don't really apply to molten salts, we can still apply the order of that as well and see which ones are higher or lower on the list. So if we look at sodium, we see that aqueous sodium picks up an electron to become sodium salt, and you can see that the electrode potential is negative 271 volts. If you look at potassium, the electrode potential is negative 292 volts. And so even though these electrode potentials don't really apply, we can see the order of the electrode potentials and determine which one is more likely to undergo reduction. And so here we see that the electrode potential of potassium is more negative than that of sodium. Another way to put that is that the electrode potential of sodium is more positive than that of the potassium. So remember, when we're trying to figure out reduction at the cathode, we want to know the one that is more positive. The one that is more positive is going to attract electrons more. It's going to have a greater tendency to undergo reduction. And so in this case, sodium is more positive, and so therefore it's going to have a greater tendency to undergo reduction. It's going to more easily undergo reduction compared to potassium. So therefore, we would predict that sodium is going to undergo reduction at the cathode. So the two reactions at the anode and cathode are written here. So at the anode, oxidation is going to occur with the chloride ion. So 2 chloride ion liquid is going to go to chlorine gas plus 2 electrons. And then at the cathode, the sodium liquid ions are going to pick up the 2 electrons and become solid salt. So this is what we would predict under for this mixture here. What if we have two salts that instead of having a common anion, they have a common cation? So that's the second example. So here we have sodium bromide and again sodium chloride. They both have sodium. So here we know what's going to be reduced at the cathode. That's going to be the sodium, since that's the only positive ion that we have. So therefore, that's going to be happening at the cathode. But we have 2 anions, so we have to figure out which one of those is going to undergo oxidation at the anode. And so again, we can use the electrode potentials for the reduction half reactions for aqueous solutions to help us with that. And again, we're only looking at the relative order of them. The actual electrode potentials aren't going to really apply to our situation for molten salts. So here we can see that the chloride ion will become the chlorine gas and give off 2 electrons. So that's going to be the reduction of the chloride ion. and that's going to be a positive 136 electrode potential, 136 volts. For bromine, we're going to have that be reduced or oxidized, excuse me, that's going to be oxidized, and that's going to give an electrode potential of positive 1.09 volts. So here, since we're talking about the oxidation at the anode, there we're looking at more negative. Which one's going to be more negative or less positive? Because remember, at the anode, it's negative, and so therefore it's going to push the electrons away. So the more negative is going to be the more negative electrode potential is going to be the more likely one that's going to undergo oxidation. So if we look here, we can see that the electrode potential of bromine, the bromide ion here, is going to be less positive than that of the chloride ion. And another way to say that is that this one is less positive, or we could say it's more negative. So this one is more negative than this one. And so therefore, we would predict that since this is more negative, this is going to repel or more likely give away the electrons or push the electrons away compared to the chloride ion. So we would predict that bromide ion would be the one to undergo oxidation at the anode. And so we write the 2Br minus liquid goes to bromine liquid, the Br2 plus the 2 electrons. And of course, sodium is going to be reduced at the cathode. Sodium plus ion is going to pick up 2 electrons and become sodium solid. And so that would be our prediction at those electrodes. So I hope this was helpful. If you enjoyed this video, if you learned from this video, if this helped you in any way, please like the video, share the video with others, hit that like button right there. Also, subscribe to my channel, hit that notification bell up there, and when you do, make sure you click all so you can be notified by all the videos I put out. Also, put a comment down below in the comment section. Let me know what you think. If you've got any questions, I'd love to hear from you. Thanks for joining me. Have a great day.